Information in practice. Data science is all about information. We're going to look first at mutual information, information that is shared between two variables. So let's recall information and entropy. Suppose X is associated with set S with a probability distribution P of X. Self-information, we're actually going to denote it by lowercase h in these videos because later we're going to have I of X semicolon Y as the notation for mutual information. Notice that we can use different bases for our self-information. Nats is when we use log base E or the natural logarithm. Entropy, this is our definition with the little h as surprisal or self-information. And there it is written out. But suppose we have another variable, y, associated with S. It's got its own probability distribution, Q, and its own self-information. So how do we compare distributions P and Q? Well, this is an extremely important question. See, training produces a model as a probability distribution Q of Y. And then testing measures how close Q of Y is to P of Y, which is approximately the true distribution. Of course, we've got the noise in the way. So we can think of this in terms of capital X and capital Y having probability distributions P and Q, and also a joint probability distribution. We can define the P then as the marginal distribution for X, and Q is the marginal distribution for Y. Recall the joint entropy is the double sum over X and little y in S of P of XY, H of XY, written out like that. And if X and Y are independent, then we show that the joint entropy is the sum of the individual entropies. But what if X and Y are dependent? In particular, if X and Y are dependent, there is information that's shared between them. And if X has probability distribution P and Y has probability distribution Q, there's information shared between P and Q. So suppose P and Q are distributions on set S. We've defined pure entropy for one distribution. Now let's define cross-entropy, which requires two distributions. Clearly, the cross-entropy of P with itself is just the pure entropy, and cross-entropy is often used as a loss function, the goal being to end up with the entropy of just P. That leads us to define Kullback-Liebler divergence. This is the difference between the cross-entropy and the pure entropy of P. It's a general method for comparing distributions. And notice the emphasis here is for comparing them. And in terms of summation and logarithms, we're given by this formula, which can be simplified to that. So let's prove a theorem that the Kullback-Liebler divergence is non-negative. Well, if f of x is negative log base 2 of x, its second derivative is positive, and therefore f is convex. But if f is convex, then it has to satisfy this definition of a convex function. And that means we get this inequality where we have the sum on the outside, the negative of that is greater or equal to the negative of the log base 2 with the sum on the inside, or that's the argument of the log. The Kullback-Liebler divergence is the sum of p sub I log base 2 p sub I over q sub I. Notice we can flip the p sub I and q sub I by putting a negative out in front. And by the definition of convexity, that's greater than or equal to the log of everything now inside the argument. But that means these p sub i's cancel. We get the sum of the q sub i's, but the sum of the q sub i's is 1, and the log of 1 is 0. So now we have proved our theorem. Corollary is that cross-entropy is always greater than or equal to pure entropy for all distributions P and Q. And model fitting is often based on minimizing cross-entropy and trying to reduce it in some sense down to the pure entropy. So how do we compare distributions P and Q? Well, cross-entropy is our initial answer. Kullback-Liebler divergence non-negative means that the cross-entropy is always larger than the pure entropy, and that gives us often a training goal of finding the Q that minimizes the cross-entropy, i.e. cross-entropy as a loss function. And cross-entropy loss functions are ubiquitous, but we need to say a lot more than just cross-entropy. So let's prove a theorem that joint entropy is less than or equal to total entropy. Here's our definition of joint entropy. Our definition of the entropy of just a variable x, which can be written in terms of the joint entropy in this way. Same thing with the pure entropy of y. And notice that if we add the h of x and h of y and subtract the joint entropy, we're going to have differences in products of these logarithms, and that's going to give us log of this fraction. But that's just the Kullback-Liebler distribution of p of xy and p of xqy, which is non-negative. So therefore, joint entropy is less or equal to total entropy. That leads us to mutual information. We define it to be the total entropy minus the joint entropy. It's the information overlap of x and y. The last line of our proof was that this was equal to the Kullback-Liebler divergence. Therefore, mutual information itself is the Kullback-Liebler divergence of the joint entropy with the product of P and Q. But that, of course, means that mutual information is non-negative. Also, the joint entropy is equal to the total entropy if and only if x and y are independent. And therefore, the mutual information of x and y is 0 if x and y are independent variables. I of yx is I of xy, and the mutual information of x with itself is just the entropy of x. So mutual information is a measure of information shared between two variables. The product of those variables would be the probability distribution if x and y shared no information, in other words, if they were independent. The joint probability distribution and the mutual information, again, is the Kullback-Liebler divergence of these two distributions. In other words, it's information shared by x and y in comparison to their independence. And again, we're comparing. Here's our formula for the mutual information given P and Q. And notice that if we have independence, if and only if we have independence, do we get the P of xy as the product. That fraction becomes a 1 and we get a 0. So let's look at something called conditional entropy. That's just the entropy of y given x, that we know what the variable x is, and that's just the joint entropy minus the entropy that we got from x. In other words, it's the entropy from xy jointly, but only that part that's due solely to y. It's the entropy due to a conditional probability distribution, the probability of y given that we know the value of variable x. We'll prove that next video. So remember, mutual information is total entropy minus joint entropy. We can rearrange that, and we get that it's h of y minus the conditional entropy of y given x. Now, the fact that the entropy is non-negative means that the mutual information is less than the entropy of y, and the mutual information is symmetric, so therefore mutual information is always between 0 and the smaller of the entropies of x and y respectively. So mutual information is the information from y that's obtainable from x, or in other words, the information shared mutual between x and y. Let's look at an example. Jane chooses from 3 cards, number 0, 1, 2. John chooses a card from the 2 that remain. X is Jane's card, Y is John's card. Well, here are the only 6 possible outcomes. And notice that they all have a equal likelihood of occurring, 1 out of 6 chance. And this is where, of course, the first one represents Jane's and the second one John's. The entropy, well, everything is a 6, so if I put a negative log base 2 of the probability, that's the same as log base 2 of 6. And I can move it out of the sum, but the sum is just the sum of probabilities. That has to be 1. We get the log base 2 of 6. Let's look at our marginal distributions. Now we have a formula for calculating those. And so we end up with a third, but there's no real surprise there. This is the probability that Jane gets a 0. But notice there are exactly 2 outcomes in S where Jane has a 0, the first 2. Similarly, we have formulas for the marginal distribution of 1. Again, we get a third, and that's the same as the marginal distribution of X for the outcome of 2. The marginal distribution for Y, similarly, we got a formula. We get a third, but we can just look and say, well, Y is 0. That means that look how many times does the second card be equal to 0 in our set S? Exactly twice out of 6 possible. So the pure entropy of X and the pure entropy of Y have to be the same. That's this negative sum, but the probabilities are all 1/3. That gives me then there for the log base 2 of 3, which means the mutual information is h of x plus h of y. That's 2 log base 2 of 3 minus the joint entropy log base 2 of 6. And we can do some simplification. And we get about 0.58496 bits. Let's look at another example, mutual information score, where we have a variable x corresponding to one set of labels and a variable y associated with another set of labels. And our example is going to be what's called car evaluation data. Here it is in Python code for it. We have grade, which is unacceptable, acceptable, good, or very good. Price, maintenance cost, number of doors, number of people that it will carry, size of the trunk, and how safe it is. And all 1,728 combinations of these were rated by people as to whether or not they had a grade of unacceptable, acceptable, good, or very good. Which features share the most information with the grade? Well, in order to do this example, let's take our concept of mutual information and make it a mutual information score. So U sub I, that's the set of observations labeled by L sub I for X, and we can take our probability that X is L sub I and take the cardinality of U sub I over N as an approximation. So V sub j is the set of observations with y equals C sub j. Q sub j, the probability that y is C sub j, is approximately the cardinality of V sub j over N. The intersection means we have an x equal L sub I and a y equals C sub j. And again, Pij, that joint probability, can be approximated by the cardinality of the intersection of U sub I and V sub j divided by N. So our mutual information formula becomes this scoring algorithm. Let's apply it to our car evaluation data. Which X shares the most information with Y? Well, if we look at all of these, we find safety has the highest mutual information score with respect to grade. So this is great. We can use information and compare things. So if X and Y are independent, there's no shared information. And if we have 2 dependent variables, then the mutual information measures how dependent in bits if base 2 or nats if base E. It's related to KL, divergence, and cross-entropy. So what are we missing? Well, we need a better understanding of conditional entropy. And that's what we're going to look at in the next video using what's called information gain.